Hi there. In this video, we will solve a case of gas well testing analysis. We will solve a case of modified isochronal test analysis or gas well derivaability analysis using theoretical or analytical method using Houpert technique. All right, so let's jump into our case. By the way, I've prepared a spreadsheet to solve or to do the analysis for the gas well deliverability. And you can see this is my spreadsheet. And in this video, I will guide you. I will do the step-by-step analysis so that we can understand how to analyze, how to compute or calculate the deliverability of a gas well. Right? We open with a table. So it's just a typical or a template table. Into this table, we will put all our gas test data. All right. We have several columns. The first one is the flow period and the duration for, if this is a modified isochronal test, then the duration for the flowing period and the duration of the shut-in period will be equal. And if you get the data, you can also input the choke size or the choke opening. And Q is the gas flow rate. And PWS is the static pressure data or the static bottom hole pressure data. You can also use it to represent the average reservoir pressure. And PWF, the previous one is PWS. S means static or shut-in, and PWF is the flowing well or flowing bottom hole pressure. All right. And the next columns, the two last columns are column for the computation. Right. Suppose we have a gas well, right? We now will discuss the case. Suppose we have a gas well and we know the depth of the reservoir, we know the depth of our well. Let's say we have a well with 6,000 feet in length, all right? And we know the diameter of our tubing, suppose it's 2.441, all right? It's a typical tubing, and we do the well testing. Before the well testing, we do the static bottom hole pressure survey, and we know that the bottom hole pressure, the static bottom hole pressure is 7,121 psia. And then we perform the modified isochronal test. For each flowing period, we will run the test for 9 hours. All right, so now I prepared 4 rows and you can follow along. The first step, the first isochronal test, I will run with 9 hours flowing period, continued with 9 hours shut-in period. So I prepare like this one, 9 hours. And let's say I don't know the choke size, so I will just delete this data. And we know the flow rate, and the flow rate is 8,584 MSCFD, 1,000 standard cubic feet per day. And then you can see this is the data. I know the data in PSIA, the static well bottom hole pressure, this one 7101. And during the flowing period, I also measure the flowing bottom hole pressure, and the pressure is 6,216. So from the PSIA, I just compute back to get the PSIG. All right. This is just for convenience. So I get this data. All right. I get this data and then I compute using this formula. So just PWS squared, this one, minus subtracted by PWF squared. I get this one. So that's easy. And also for this method, theoretical method, I calculate this parameter, PWS squared minus PWF squared, and then they are divided by the flow rate. So it's easy. I just use this one, this cell divided by the flow rate, this one, right? So it's very easy. I just want to make the color. All right. It's very easy. And then the second one, the second flowing period for 9 hours followed by 9 hours of shut-in period. So it's like this. And I measure the flow rate. The flow rate, for example, is 9,879. And I measure the static bottom hole pressure during the shut-in period, 7,085. And during the flowing period, I measured the flowing bottom hole pressure being the 5,965. All right, so that's easy. And using this formula, by the way, it's very easy. So it's just PWS squared minus PWF squared. So it's like this. I can drag this one. So I maintain the formula. Also this one, the same. And then for the third period, again, the duration will be 9 hours, flowing 9 hours, shut-in 9 hours. And then the flow rate is the 14,000 MSCFD. All right. And then let me color this one. And then the flowing, this value. And then, I mean the static, this one, 7,070. That one is for static, and for the flowing, 5,071. So that's easy. Okay, so this is the isochronal test. And then I do the stabilized well testing, stabilized flow to reach the pseudo steady state flow regime. And I flow my well at 36 hours. So I make this one 36. So that's for the final step. And then I do shut-in. For example, you can do shut-in for 36 hours or even longer than that in order to get the best static bottom hole pressure representing the average reservoir pressure. For example, I shut my well in for 24 hours. So let me type in like this. Okay, to represent 36 hours of flowing and 24 hours of shut-in. Okay, you can design your table as per your preference. All right, for example, the flowing period gives me 13,000 MSCFD, and I measure the static bottom hole pressure during the shut-in, 7,121, and the flowing period gives me flowing bottom hole pressure of 5,119. By the way, I get the data in PSIA, absolute PSI, and for PSI gauge, you can easily calculate by subtracting this value with 14.7. Okay, so I get this one, and also for the flowing minus 14.7. Okay, so that's super easy. And then we create this plot. So for this plot, for the horizontal axis, it's the flow rate. Okay, so this is the technique using this Houpert technique. So for the horizontal axis, we plot the flow rate in MSCFD. And for the vertical axis, we plot this term, PWS squared minus PWF squared divided by the flow rate. Okay, so yeah, I plot, and I plot these 4 points, and I calculate the trend line. So if I right click and select data, okay, this one, I can remove first like this. All right. And then select data, add. All right. You can see the axis. The X, the horizontal axis is the flow rate, this one. And for the Y axis, the Y or the vertical axis is this column. So you get that one. And you can touch these dots and right click and add trend line. Wait, this one, trend line, and then display equation on chart, display R squared. And we get the R squared of 0.8273, which is quite good for our trend lining. And I just want to color it red, and it's quite thick and dashed. Want to make it quite thick like this. Okay. And I want to make this bigger. Sorry. Let's say 15 because this is important. All right. Okay, so we get this linear trend, linear equation, and I make this formula as per the technique. So it's like this. So you can use PR, which means the average reservoir pressure, or you can also use PWS or static bottom hole pressure. They are actually the same. Average reservoir pressure represented by the static bottom hole pressure. They are quite the same. But for the sake of this video, I can use PWS instead, like this. All right. So PWS squared subtracted by PWF squared equals to A multiplied by flow rate plus B multiplied by flow rate squared. All right, so that's the first equation. And for the second equation, we divide the left-hand side by the flow rate, and also the right-hand side, we divide with the flow rate. So the remaining equation will be this one. Sorry. PWS squared minus PWF squared divided by the flow rate equals to A plus B multiplied by the flow rate. And this is our main equation. And we can look at this equation from this trend line result. All right. So you see here in this equation, we get value of 0.0832. And this one, the intercept, 671.56. All right, and look at this equation. So here in my second equation, A is the intercept. Okay, and you can check the note. The constant A is determined by using the stabilized data point. Okay, stabilized data point, and the constant B is established from the slope of the plot of PWS squared minus PWF squared divided by flow rate versus the flow rate, which is the slope of this plot. All right, so B is the slope, and we can directly use this value, 0.0832. All right. And for the A part, the constant A is determined by using the stabilized data point. And the stabilized data point is actually this one, the flow rate of 13,000, this one, okay, this one. So yeah, we need to calculate that part first, and we can calculate that by using this step. So this one, if we copy and or maybe I make another row like this, and let's say I just copy and paste. So to calculate A, we can just put this one to the left hand side. Okay, so you get A, but we will use the flow rate from the stabilized data point. So A is this one, okay, minus B, all right, multiplied the flow rate at stabilized step, which is 13,000. Okay, so that's very easy. The constant A is 803.36. Okay, and then let's read it with me. Solving this equation for the absolute open flow or the flow rate when the PWS minus PWF, or sorry, this one, let me change it first. Okay. Okay. Solving this equation for the AOF, absolute open flow, or flow rate when the PWS squared minus PWF squared equals to PWS squared minus this one, 14.7 or 14.65 squared, because the absolute open flow or maximum flow rate will occur at flowing bottom hole pressure of 0. All right. So yeah, let me, okay. So we deal with this one first. We get this PWS at stabilized data point, 7,121 squared, but minus 14.65 because we want to achieve absolute open flow. All right. We will deal with this one first. Okay. And this one is PWS squared minus PWF squared, but the PWF is 14.65 because it's absolute open flow condition. But for the PWS squared, we use PWS at this one, 7,121, which is the static bottom hole pressure after stabilized flow. And we get this static bottom hole pressure after shutting in the well for 24 hours. So this is the best static bottom hole pressure for us. Okay, and the result is this one. Okay, and then we will calculate this. We will also calculate this one, but we will use this formula. Okay, so you can follow me. So C43, so it's the A, okay, multiplied by the flow rate, this one, multiplied by the flow rate, but the flow rate will be absolute open flow. So D49, this one, the absolute open flow, plus B, and B is this one, 0.0832 multiplied by AOF squared. And the value is this one. Okay, but make sure that the value here and there should be equal. And we can achieve that by using iteration by changing this one, the absolute open flow. So at this time, this AOF is still wrong, and we will do iteration in such a way that this one should be the same with this one. So in other words, we want to find the absolute open flow. Okay, and we can do that by using what if analysis. Okay, here. So what if analysis is in data, and what if analysis goal seek. All right. So I want to set this cell to value of 50 million and 708,426 by changing the absolute open flow. All right. So let's click OK. All right. So the absolute open flow is 20,327 MSCFD. So we get the same values, right? So this is our AOF, our absolute open flow. So that's quite easy. And the last step will be to construct the deliverability curve. So I prepare the table. The first column will be this one, the static bottom hole pressure. Okay, but let's use this value because this is the main static bottom hole pressure. And the next one is the flow rate. And the last column is for the flowing bottom hole pressure. All right, sorry, it should be format cell subscript. It should be subscript as well instead of superscript. All right. So the easy way is like this. Okay. This one, the LF multiplied by 0% and multiplied by 10% and so on and so forth. And the last one is 100% of the AOF. So yeah, that's for the flow rate column. And for the PWF, now it will be calculated. How do we calculate the PWF? Yeah, it's quite easy. You can check the formula here. All right. So you can just rearrange this equation in such a way that you can calculate the PWF. All right, but make sure that you do the square root because in this equation, we have PWF squared. Okay, so let me guide you instead. So let me copy and paste this one. So, or maybe this one. This is easier. So it's quite easy. It's very easy actually. So PWF, sorry, PWF is, let me put you there. And then this one, I put you there. All right. Okay, and then maybe it's better to look, yeah, this one. And then let me do the, yeah, just for proper writing. Subscript, superscript, and then, yeah, I can erase the G. Okay. So this one for the PWF squared. So if you want to get the PWF, you can just do square root, SQRT of all these terms, and then I can erase the square. All right, so this one is quite easy to get the PWF. All right, so yep, so let's do that here. So we do the square root by using this powered by 0.5. And then this one, PWS squared. So PWS here, I use 7,121 squared, and then minus this one, minus A multiplied by the flow rate from the previous column, plus the B multiplied by the flow rate squared, flow rate from the previous column. All right, and don't forget, everything will be square root, all right, or powered by 0.5. Okay, and then you can just drag and you can get the solution. Okay, and maybe I can expand this like this. All right, and then we can also plot the well-test data. I use this one. I just call the data, the well-test data from this table. So for the flow rate equal, and then we can just do this and drag like this. All right, and then, sorry, PWF, I mean, PWF is this one, and then drag them down. You get this one, and then the flow rate, this one. So you can see the well test data overlays almost perfectly, okay, with the deliverability curve or IPR curve. All right, so I can, yeah, I call the data points here, can do like this, and then the deliverability curve or the IPR curve, just do like this. And this plot we construct by using flow rate at the horizontal axis and pressure at the vertical axis. Okay, if you are not sure, I can delete like this and then select data. Let's call it IPR. The Q, the X will be the flow rate, and then the Y, the vertical, will be this one, the pressure. So we get the IPR, and then we also plot the data point test, right? X and then Y, the pressure. So you get that. And maybe you want to make line from the IPR. So right click, format data series, and touch this one, solid line. Let's color them yellow. And then the marker, I want to use no marker. So I get perfect line like this one. And maybe I can color the data points. I want to use circle and then red like this. That's for the border, and for the filling also red. So you get like this. Okay, so that's, yeah, that's very easy. So that's the solution. That's how we construct the deliverability plot from our gas well using the gas well test data. Okay, so that's all. I hope this video and this solution is useful for all of us. All right, see you again. Thank you.